We are now proceeding with the paper from KU Leuven. It is entitled Development of a Membrane-Shaped MR-Based Composite Draping Tool, and it is authored by Gert Schouterden, Jeroen Cramer, Demeester, and Karel Kellens from KU Leuven. We are looking forward to see that paper presentation now.
Hello, my name is Gert Schouterden from the KU Leuven campus Diepenbeek. And today I will be presenting our newly developed and membrane-shaped MR-based composite draping tool. First, I will be going over the state of the art and how we came to the development of our tools. Next, I will be presenting the two tools we developed and how we evaluated them, finishing off with a short discussion and a conclusion. Composites have become more often the material of choice for a large range of applications. This can be mainly devoted to their high strength-to-weight ratio, their good chemical resistance, and other good characteristics. And for some production scenarios or products, automation is available. However, these are often very expensive purpose-built machines that are not able to cope with really complex geometries. So what do we need to do when we want to make these complex geometries, when we want to function in high-mix, low-volume scenarios like, for example, automation for SMEs? These scenarios are still dominated by a lot of cost-intensive manual tasks, mainly due to the difficult handling properties of the material and the high variety and complexity of the product contours. In industrial automation, these problems are often answered by cost-increasing multi-robotic systems with a lot of degrees of freedom, or just by making a lot of or a large range of feature-specific tools. Because of this, there's still a large threshold on SMEs to implement these composite automation solutions in their flexible, high-mix, low-volume production scenarios. Because of this, advancements in composite material handling technology are needed. When we're talking about these advancements, we are looking for a system that can ideally perform three main tasks. First, the gripping and transporting of the fibers from the supply to the mold. Secondly, the actual draping of the fibers. And lastly, the optional fixating of the fibers with, for example, a heat-activated binder as seen in preforming processes. The existing setups we can divide up into four main categories. First, the reconfigurable mechanisms, equipping grippers that can pick up fibers from a flat supply and change shape to the shape of the mold. Secondly, flexible substrate systems, often consisting of a foam with integrated grippers that drapes the fibers by the deformation of the foam. Thirdly, pixel-based systems, equipped with a lot of small grippers that can be individually controlled and move independently of each other to adapt to the shape of the mold. And lastly, the deformable membrane-based systems, which for example consist out of a granulate-filled bag of which the deformability can be controlled. Next, we can go and look at where all of these systems meet their limitations. The reconfigurable mechanisms are good at coping with light curvatures over large molds. They meet their limits in smaller, more complex molds where the needed degrees of freedom and the deformation increases the complexity and cost of the tool. Also, these tools are not able to cope with small features on a large surface. The flexible substrate-based systems meet their limits in a maximum formable feature depth caused by the foam's compression characteristic. As seen in the image, the fibers on the top part of the mold are clamped in heavily, whilst the draping force of the expanding foam in the middle decreases. The pixel-based systems are limited by the feature size that determines their pixel size, thus also the complexity and cost of the tool. We also see some potential problems when trying to use these tools on features which have near vertical walls. Lastly, the existing deformable membrane systems are more versatile in adapting to different shapes and controlling their draping force. However, there's still one main action seen in the manual draping process none of these tools has been able to reproduce: locally applying a force in a continuous manner by selectively fixating the remainder of the fibers. In this manual process, this action is performed with the smart and very flexible hands and fingers of the worker, aided by some tools. If we would be able to get closer to the characteristics of these manual actions, we would be able to first achieve an overall better draping result in complex mold. We'd also be able to cope with a larger range of features, and we would be able to get more control over process parameters as, for example, the shearing of the fibrous material. In this paper, we propose two new membrane-shaped systems that aim at imitating this complex manual action. On one side, we have the water-based tools, that shows some promises for human-robot calibration, and on the other side, we have a magnetorheological tool that uses magnetic attraction force as a draping force, and this tool shows a lot of potential for full automation. From a previous analysis, we can conclude that for 3 previously mentioned functions, the draping step is still the most challenging. Consequently, this is also the step that we will focus on in this paper. When we go and look at what the requirements of the tool are, we see that we want a tool that can adapt to all shapes and sizes of the mold without a problem. Whilst doing this, it should also apply a continuous and even overall force that serves as an overall fiber fixation during the draping process. This characteristic we describe is the characteristic of a liquid, thus we went for a liquid-based tool. The further requirements of this liquid are also that it needs to have a low viscosity to ensure operational speed. It should also be inexpensive, and ideally it should be harmless to the fibers in case of a leak. Next, we also need a membrane to contain this fluid. The requirement of this membrane are that it should also be easily deformable to the mold surface. The contact surface may not be sticky to allow slippage between the fibers and the membrane, and also silicone cannot be used due to the risk of contamination. Lastly, we also need a way of specific force applications to specifically drape or fixate the fibers. And lastly, just a remark, we are currently only focusing on the draping of dry fibrous material, like for example in LCM or Vary processes. Next, the actual design of our tools. So I have a fluid-filled membrane that's made of high-density polyethylene with a thickness of 30 micrometers. This is a balance between formability and its strength or durability. This membrane is mounted on an aluminum frame, which results in a working area of about 450 by 350 millimeters. The tool is shown in the pictures both in its transport and in its draping position. Like mentioned before, in this paper we propose 2 different tools. The membrane of both tools is the same. In the first iteration, we fill the membrane with water. And the local force application can be done in 2 ways. It can be applied by a human or by a robotic system. In the first case, the tool will serve as an assistive tool for the manual process and serve as a universal clamping tool providing overall fixation of the fibers. Additionally, the membrane will support the fibers when the human applies local force. This way, the risk of causing unwanted distortions is decreased. Meanwhile, the transparent back allows the worker to see what he is doing to the fibers in the mold. In the other case, when a robotic system applies the local force with a flexible substrate and effector, in this case we still have all the advantages we mentioned before, but we also still need a large range of feature-specific tools to mimic the function of the human hand. Full automation still seems far away in this case, but we still see some potential for human-robot collaboration. In our second design iteration, we will fill the membrane with MR fluid. Here we will be applying a local force by magnetic attraction of the magnet on the other side of the mold. This attraction force poses some interesting characteristics. You are attracting a fluid to drape the fibers, thus you also have a tool that's infinitely adaptable to all features. Also, this attraction force is well controllable and inherently compliant. In this local force application, we have found a potential low complexity equivalent for the force application by the human hand in a draping process. Hereby, we have also potentially opened the way of cost-effective full automation of some manual draping processes. However, there's still a drawback that non-ferromagnetic thin molds are needed to use this approach. When we go and look at the composition of our MR fluid, we have round-shaped iron particles between 1 and 5 micrometers dissolved in a thicker EP680 oil that we chose to improve the sedimentation stability. And we have them mixed with each other with a mass percentage of a mass fraction of 22% iron powder. Next, we want to test our newly developed tools. We draped 1 layer of a generic trill-woven glass fabric in 3 different molds: an MDPE lid mold, an aluminum conical bowl mold, and a composite air grabber mold. Next, we analyzed our results that we got. We visually inspected the fiber orientation and the distortions, and we also took some 3D images of the empty molds and the molds with the fibers draped in them and compared them together. Overall, we can conclude that both the water and MR-based tools delivered satisfactory results. No systematic irregularities of fiber orientation and distortion were noticed. The most important conclusion that we can draw from this test is that the draping strategy or sequence has not become irrelevant but still is of utmost importance to achieve a satisfactory result. Another important remark needs to be made with these 3D scan results. These show the height difference between the superimposed point clouds of the empty mold and the mold with the fibers in it. Due to the needed smoothing and filtering to alleviate the negative effects of the reflection of the glass fiber and the camera accuracy, we must warn you to interpret these absolute height differences with caution. However, the height differences between 0.2 and 1 millimeter can be assumed to be perfectly draped areas. First mold that we tested is the lid mold. Here we'll see an NDP mold with some stiffener ribs inside of it. First remark that I need to make, the red areas, so the problem areas in the middle of the mold, you can just ignore. These were parts of the fibers that were outside of the working area of the tool. When you look at the rest of the draped area, you can say both tools performed quite well. However, the MR-based tool performed a little bit better. It was better at adapting at the small radiuses at the bottom of the stiffener ribs, and it was also better in performing with the double curved surfaces. However, you can see with the MR-based tool in the left top corner, there's still a problem area. This was mainly caused due to a stiffer area in the back, which was caused by weld lines in it. Going to our second test mold, again we can conclude that both tools performed quite well regarding the difficulty of the mold. However, we still saw some problems with the water-based tool when trying to drape the small radius on the top of the cone. Here we again had some problems when pushing through 2 layers of the membrane and the fibers themselves that you couldn't quite completely form the small radius with your fingers. However, when we were comparing both of our tools to just a manual process without any help, we still saw that both of our tools provided some advantages in the even holding force, reducing the amount of wrinkles and making the process faster. And also, just the supporting nature of the membrane resulted in less distortions in the fibers. Looking at our third mold, our MR-based tool performed worse. This can be mainly devoted to 2 main factors. First, the mold thickness, limiting the draping force, and secondly, the local bridging of the membrane due to the forming of 2 fluid pockets on the outside of the mold. This puts tension on the membrane in the center, thus preventing this feature from being draped as shown in the figure. This was more seen with the MR-based tool because of the slightly smaller fluid content of this tool than a water-based tool. To alleviate this problem, the tool's membrane should always be contained from all sides, and also the fluid volume should be higher than the highest feature in the mold. Also, we noticed sometimes some unwanted distortions with removal of the tool. This could happen if, for example, the tool wasn't removed perfectly vertically. Also, if the membrane, for example, became sticky due to leakages, or if we were draping a feature which was very deep and had vertical sides. Overall, we can conclude that the testing results were satisfactory. However, there's still a lot of room for improvement. So, for example, on the side of the tool, we could be integrating the 2 other essential functions we mentioned in the beginning. So, integrating a gripping system and integrating, for example, heating pads for the working with heat-activated binders. Also, our MR fluid could be optimized a lot, so improving sedimentation stability, or for example, going to an MR elastomer instead of a fluid. Also, the automation or the full automation of our MR-based tool is something that we're currently working on, as seen in the video. Other research tracks are looking into thin non-ferromagnetic molds that we need for our MR-based tool. So for example, looking into preforming, thin composite molds, or additive manufacturing. Future testing we will be conducting is, for example, the influence of multi-layer draping, sequential or simultaneous, the influence of gel coats, the influence of different materials or different weave types. Also, we will be looking into the optimization of our draping strategies, so just the manual pad planning of the robot like it is now, or for example, going to automated part generation by, for example, feature extraction from the mold. Overall, we can conclude that both of these tools have proven their potential. In the case of the water-based tool, this is as an assistive tool for the manual draping process. where it will serve as a universal holding tool and support the fibers, reducing the chance of causing distortions. In the case of the MR-based tool, we've potentially found a replacement for the human hand as a force applicator in the draping processes, thus creating some opportunities for the full automation of these processes even in these difficult high mix low volume scenarios. Additionally, there's still a large room for improvement. Thank you for your attention. If you have any questions, feel free to ask or contact me on the address below.
Thank you, Gert, for doing the presentation and the paper about the composite draping tool. We're now getting live two of the authors into our live stream for the question and answers. Hello, this is Franz Dietrich from Berlin. Can you hear us?
Hello, Franz. Nice to meet you.
Thank you. It's clear here in Berlin for you. Thanks for doing the presentation. Thanks for doing the paper. I'd like to start with you in the discussion about the fluids that you have used. Can you point out again about the advantages and the disadvantages you see for water and for the magnetorheological fluids, particularly when it comes to leakage or when it comes to the preparation of the fluids?
Of course, when we look at both tools, like we also discussed in the paper, we have made our two ways. One side, the water-based tool, where we only use the water to perform an overall holding force to assist the human. This is the disadvantage that still a human is needed to apply this local force. When we go to using our MR fluid, we also still apply an overall holding force to hold the fibers in place and support them by the membrane. But when we, for example, go and use a magnet at this moment, that's on the bottom side of the mold, we also can apply an inherent compliant force on the fibers themselves to specifically drape them in that area. Also, going to the composition of our MR fluid, at this moment we are still at a very basic point. We just are mixing a thicker oil with our iron particles. There's still a lot of room for development for that at this moment, so we still have some problems with sedimentation. But also, like we mentioned in the future work, we are looking forward to improving this fluid, or also maybe even looking into going to MR membranes, so membranes that include the particles, the iron particles in them themselves, so that we can attract the membrane and, for example, then also fill the membrane itself with, again, water, which is a lot less expensive. There's a lot less of a problem when, for example, the bag is leaking.
Okay, so when I personally work with magnetorheological fluids, I remember that abrasion becomes a problem over time. Have you looked into that aspect already?
Yes. Like I said before, the sedimentation is still a problem for us, but the biggest problem or the biggest disadvantage from our technique at this moment is still that we need thin molds to have sufficient magnetic force strength to attract our MR fluid.
Yes.
That's one of the disadvantages. I also want to say, on the other side, also at this moment, we are not using the stiffening up effect of the MR fluid. So when the magnetic field is applied, that the fluid stiffens up. That's a characteristic that we are at this moment not using to its full potential. It's still something that we're thinking about in the future. At this moment, we are only using the attraction force. Also, we at this moment have chosen to go for a permanent magnet just for the higher magnetic field density. To increase our draping force. We've seen still with these electromagnets that it's still often a problem to apply enough force.
Okay, so good luck with the further development of that. Thanks for answering the questions. Thanks to the colleagues from Leuven for being here in that session.
Okay, thank you.
Goodbye.
Goodbye.
Bye.
So this was the presentation and the question and answer session for the paper Development of a Membrane-Shaped MR-Based Composite Draping Tool, authored by Gert Schouterden, Jeroen Cramer, Demeester and Karel Kellens.